So now let's jump into Module 6.2. Within Module 6.2, we're going to take a look at the bioheat equation, discuss the thermoelectric power generation, then also look at conduction through thin gas layers and through thin solid films. So activities within this module here, we're going to take a look at some of the governing equations associated with these topics here, go through some practical applications, and then do some actual problem solving and look through some of my hand solutions to these problems. So as related to our textbook, this is Chapter 3, Sections 3.7 through 3.9. So we're wrapping up Chapter 3 with this module here. And again, the topics we're going to consider here are the bioheat equation, thermoelectric power generation, and micro and nanoscale conduction. So as we continue on now, we're going to discuss our bioheat equation. In particular, let's take a look at the nature and rationale of this bioheat equation. So heat transfer within the human body is affected by two different volumetric thermal energy phenomena. One of these phenomena we're going to discuss here is the metabolic heat generation, and the other is exchange between tissue and flowing blood, or what's known as perfusion right there. So therefore, if we have one-dimensional steady-state heat equation describing the local temperature, our Tn right there, for example, a living tissue may be written in terms of the following bioheat equation shown down here in equation 3.111 in our textbook right here, where we have our d squared T over dx squared, or our second derivative of our temperature with respect to the position x right there, plus we have here on our numerator, we have our Q dot M, or the metabolic volume generation. So we can see over here our Q dot M is the metabolic heat source term right there. And we have our Q dot P, or perfusion right there. So this Q dot P is a perfusion heat source term right there, where perfusion within a small volume of tissue is going to be described in terms of the blood temperature in small arteries entering the volume, or what we're showing here is our T sub A. Now that leads us down to this equation 3.112 in our textbook right here. So we can see we have our Q dot P. If we go back up here, this again is the perfusion heat source term. This is equal to omega, which omega is the blood flow rate in meters cubed per second per tissue volume, which is in meters cubed right there. This is times right here, what we have here is our rho and our C right there, where this is our blood density and our specific heat right there, times our temperature difference between TA minus T, where again our TA right here is the blood temperature in the small arteries entering the volume right there. So this leads into this governing equation we see now in equation 3.112 in our textbook. Now, an assumption that we make here looking at this temperature T when we write out equation 3.112 is that the blood flowing exits the local tissue at a temperature of T that we see right there. So now continuing on with our bioheat equation right here, if we define an excess temperature by the following relationship over here, that our theta is equal to T, where T is our local tissue temperature, minus our T sub A, where T sub A is the blood temperature in our small arteries, minus this term right here, where we have on the numerator over here, we have that our Q sub M is the metabolic heat source term right there. All over on our denominator down here, we have our omega, or our blood flow rate per unit tissue volume, times our density, our blood density, times our specific heat right there. So with this relationship here, also with the parameter that we have over here for our definition of our m tilde squared right there, which is equal to omega times that blood density times that specific heat over K, what we can do is then go back to our equation 3.111 that we saw, plug those relationships in, and this now becomes the equation that we see here in 3.114, where we have our d squared theta over dx squared, or a second derivative of theta with respect to x, where our theta is defined up here by this relationship right there, minus our m tilde squared theta, which is our m tilde squared right there. This is equal to 0. So this goes back again to this equation 3.114. Now what we can notice from this relationship here is this is identical to the equation for fins of a uniform cross-section. So if we go back earlier in our chapter to equation 3.69, our textbook, we can see that same relationship right there. So therefore, the results that we've seen in this section 3.6.2 and that table that we saw before in 3.4, or table 3.4, these may be applied to solve the bioheat equation as well, due to the fact that this equation 3.69 for the equation for fins of uniform cross-section is identical to that 3.114 that we just derived here from our bioheat equation. So now let's apply some of these theories and equations to an example problem. So let's take a look at example problem 3.116 here. In this problem here, they're asking us to consider the conditions of the example 3.12 in our textbook for an air environment, except now the air and the surrounding temperatures are both at 15 degrees. Now they tell us that humans respond to cold by shivering. Now this shivering is going to increase the metabolic heat generation rate. So what they're asking us now is, based upon that, what would the metabolic heat generation rate per unit volume have to be in order to maintain a comfortable skin temperature of 33 degrees Celsius under these given conditions? So now we can reference back to example problem 1.7. So we can see here the temperature at the inner surface of the skin fat layer was given as 35 degrees Celsius. Now in reality, this temperature depends upon the existing heat transfer conditions, including phenomena occurring farther inside the body. So what we're going to do now is we're going to consider a region of muscle with a skin fat layer over. At a depth they give us here as L sub m is equal to 30 millimeters into the muscle. Now the temperature can be assumed to be at the core body temperature of T sub C, or for core, equal to 37 degrees Celsius. Now the muscle thermal conductivity is given to us as K sub m, m for muscle right there, is equal to 0.5 watts per meter times Kelvin. Now the metabolic heat generation rate within the muscle is given to us as a Q dot sub m is equal to 700 watts per meter cubed. They also tell us that the perfusion rate is given to us as our omega is equal to 0.005 in units of inverse seconds right there. And the blood density and the specific heat are given to us as, we can see here our rho sub B is equal to 1,000 in units of kilograms per meter cubed. And our C sub B is equal to 3,600 joules per kilogram times Kelvin. They also tell us that the arterial blood temperature, or T sub A for this case, is the same as the core body temperature. So T sub A is going to be equal to that T sub C that they gave us up there as 37 degrees Celsius. Now, next they tell us that the thickness, emissivity, and thermal conductivity of the skin and fat layer are given in example 1.7, so we can reference back to 1.7 for all that information. Now, perfusion and metabolic heat generation within the layer can be neglected. So we wish to predict the heat loss from the body and the temperature of the inner surface. So that's again telling us what to find. We want to find that heat loss rate from the body and the temperature at the inner surface of the skin fat layer for air and water environments of example 1.7. So now I want to reference back to the example problem they told us to look at in that problem there, which is example 1.7. So we go back to chapter 1, take a look at 1.7. We can see in this problem here, they tell us that humans are able to control their heart production rate and the heat loss rate to maintain nearly a constant core temperature of that T sub C right here is equal to 37 degrees under a wide range of environmental conditions. Now this process is known as thermoregulation. So from the perspective of the calculating heat transfer between the human body and its surroundings, which is now why we're coming into this when we're looking at our bioheat equation, we focus on the layer of skin and fat, with its outer surface exposed to the environment and its inner surface at a temperature slightly less than the core temperature right there. So our T sub I is equal to 35 degrees Celsius or 308 K. So now they want us to consider a person with a skin fat layer of thickness is equal to L of 3 millimeters and effective thermal conductivity of K value right there. The person has a surface area of A is equal to 1.8 meters squared and is dressed in a bathing suit. The emissivity of the skin is given to us as epsilon is equal to 0.95. So this is just to go back and reference some of the information they've given us in 1.7. Some of this will be changed as we're doing our problem here, but it's always good if they tell us to reference it, go back and see what information we need to utilize from this problem when solving our problem. So now that we've had the opportunity to read through the problem statement for our problem we're working on, look at all of the information given in the previous example problems, now what we want to do is create our setup page. So as we create our setup page right here, I have this for problem number 3.116. It's just really important to do because not only was the actual problem 3.116 rather wordy and a lot of information given within it, but also it told us to reference a couple other example problems as well as we were going through. So we want to make sure that we write down everything correctly and cover all 4 areas we want for our given information. So we want the variable name, we want the numerical value, we want the units associated with it, and then again how it relates to our problem there. I also want to go ahead and create a diagram as well, which we can see over here. I have my given diagram as well, so my muscle, my skin fat layer, and my surrounding layer as well. So I'm going to call this L sub m, L sub f, and over here is our air right there for our surroundings right there. So we can see here we have our T sub A right at this point here. We have our T sub S right there. We have our T sub I right here like that. We have our temperature of our surroundings there. So we have all of our information. There's a temperature of our air, of our fluid around there, our H value, our emissivity right there. Then within our muscle, we have all the given information. Within our skin and fat layer, we have all of our information right there. And as you notice with these here, for the most part, other than my epsilon value, I've left out my numerical values here and just left it in terms of variables, where I've defined those variables with their appropriate numerical values over here under the given section here. So again, there's a lot of information. So having the setup page is really important because trying to reference back to 3 different problems right here, 3.166, then our 2 example problems that references as well would be a bit of a nightmare. So this is where it really is important to create this setup page right here. So we start going through all those different problems right there and writing everything down. So the first thing we see here, let's write down our temperatures right here. So we have our surrounding temperature right here. So our T surround is equal to 15 degrees Celsius right there. And immediately I want to convert that to Kelvin to 288 Kelvin. So everything is one spot, one unit we're going to use that we can reference back to. Then I have my air temperature here. My air temperature right here is going to be my T infinity here is equal to my 15 degrees Celsius right there, or 288 Kelvin right there. Then I have my skin temperature right here, or my T sub S is equal to 33 degrees Celsius or 306 Kelvin when I do the conversion. And I also have my core body temperature as T sub C, and this is equal to 37 degrees Celsius, or in Kelvin, this is 310 degrees Kelvin. Now I want to take a look at the depth into the muscle. So this is given to me at my variable L sub m, 30 millimeters. I'm going to convert this to meters, 0.03 meters in the depths into the muscle right there. And I have my muscle thermal conductivity. So my K sub m is given to me as 0.5 in units of watts per meter times Kelvin right there. Then I have my metabolic heat generation within the muscle right there. So again, my subscript, you see my M right there. So my Q dot M is equal to 700 watts per meter cubed right there. Then I have my perfusion rate right here, given to me as omega is equal to 0.0005 units of inverse seconds. Seconds to the -1 right there. I have my blood density here, given to me by rho sub B as 1,000 units of kilograms per meters cubed. So you say I'm really paying attention to my unit analysis all the way through this. Then I also have information on my blood specific heat. So this is my C sub B, and this is equal to 3,600 joules per kilograms times Kelvin right there. And I have my arterial blood temperature right here, or my T sub A. This, I said again, was equal to my T sub C. So T sub A is equal to T sub C, which I already have up top, and I'm redoing it out down here separately, of 37 degrees Celsius, and that goes to 310 Kelvin right there. My emissivity right here is given to me as my epsilon of 0.95 unitless. Then I have my skin fat thickness right there. So my L sub SF, skin fat right there, is 3 millimeters or 0.003 meters. So again, I want everything in the correct units right here, so I convert that to meters. Then I have my thermal conductivity of that skin fat layer right there. So you notice I did my muscle and my skin fat layer separately right there. So my K sub SF is equal to 0.3 in units of watts per meters times Kelvin. Then I also have my convection heat transfer coefficient right here now for air right here. So I put that in. H is given to me as 2 watts per meter squared times Kelvin. Then I have my Stefan Boltzmann constant I'm going to need right here. So my sigma is equal to 5.67 times 10 to the -8 in units of watts per meter squared times Kelvin to the 4th. And then I have down here my surface area, and this is from example 1.7, which we can reference back in the textbook. I've also included it here in these slides to page 28. So our area right there from that problem right there, where we need to go back to example 1.7, is 1.8 units of meters squared. So now I have all of my information, and it's a lot, right here on my setup page, along with my diagram to clearly labeling, okay, this is my muscle layer, this is my skin fat layer, these are all my variables related to that. I can come back over here to my given section, take a look at each of those individual values right there, and plug them in over here to understand what's going on. So from this information here, we can then go ahead with our solution. So now as we begin our solution here, we want to make a couple different assumptions. A couple of things we're going to assume here are that it's steady state, one-dimensional heat transfer. We're going to have uniform metabolic heat generation within the muscle, uniform arterial blood temperature, uniform blood properties in general, and a uniform thermal conductivity throughout it. We're also going to assume that there's no generation in the skin fat layer and that the solar irradiation of the skin is going to be negligible. So with that information, looking back all of our given information, what they asked us to solve for, we can see that our governing equation we can use is equation 1.10 in our textbook on page 11 right there. So we can use that as our governing equation right here, where we have our Q is equal to HA times our temperature difference plus our epsilon times sigma times A times our TS and our T surrounding to the 4th temperature difference right there. So when we plug this in, this is for convection right here. For our convection term, this comes from equation 1.3a on page 8, and our radiation equation over here comes from equation 1.7 on page 10. So we can see everything we've learned in the previous chapters, previous modules leading up to this point are still applicable. And it's still great to go back to that very, very general equation right here and plug in for our specific problem, even as we get further and further along within this course. So we can also see where's our E right here. Well, E is our emissivity right here. We have a value for that of 0.95, so we can plug that in for that there. And our sigma right here is our Stefan-Boltzmann constant, which we also have a value for, given right here, that 5.6 times 10 to the negative 8 in watts per meter squared times Kelvin to the 4th right there. So from there, with those two known there and our other values that we can have, again, from our setup page that we wrote down here, now that they're all in the correct units because we took the time to do that, we can plug in all those known values to this governing equation up top here. So as we do that, we can see that Q is equal to, we plug in our H value there. Our H is 2 watts per meter squared times Kelvin right there, times our A value is 1.8 meters squared. So we can say meters squared cancel there, times our temperature difference between TS and T infinity, that's 35 minus 15, or in Kelvin, we can convert that to Kelvin, do the difference right there, get our difference in our temperatures there now. And we can see now this is plus our value here for emissivity, which was given to us as 0.95 times Stefan-Boltzmann constant, times right here our area again, that's at 1.8 meters squared. And again, we can start doing some unit cancellations out here. Then we have our temperature difference over here in Kelvin between T sub s and our T surround right there to the 4th right there. So we can take a look and make sure we cancel out K to the 4th there, K to the 4th there, numerator and denominator. So what we end up with when we do our unit analysis, we got our value up here in watts when we do our units out. That's correct. 64.8 watts from our convection portion of the equation and 183.05 watts if we take a look at our radiation portion of the equation right there. We can add those two together and now get a Q value equal to 248 watts. Those are the correct units that we're looking for there. So now the next thing we want to do is look at equation 3.4 on page 114 of our textbook there. And we get the relationship right here that our Qx is equal to our thermal conductivity times the area over L times our temperature difference here of TS1 and TS2. Now this is in general form and we'll need to apply this for our individual temperatures that we're interested in for our problem. But for now, let's just rearrange this and solve this for our TS1 right there, which is what we're going to be interested in. So we can rearrange this slightly. We can move things around. We take this term right here, divide it over the other side, and what we end up with is our Qx times our L over our K times our A value right there is equal to that temperature difference right there. Now we want to get this on our own right there. So then we can move this back over to the other side and we end up seeing now TS1 is equal to our TS2 plus now that ratio right there of QL over our KA value right there. So for our problem here, let's plug in our specific variables, and this is great while we have that setup page so we can plug back in. Our TS1 is really our T sub I. Our TS2 is our T sub S. We have our Q term right there. Then we have our L is our L for the skin fat layer right there. And our K is our K for our skin fat layer right there as well. And then we have our area that we can plug in that was given to us in the previous example, 1.7. So we have that there. We can see TI is located right there. That's the interface between our muscle and our skin fat layer right there. And we have our TS as our outer surface of our skin fat layer. So we're going across this skin fat layer is what we're interested in right now right there. Then we have our Q value right there that we can plug in for. We solved for our Q value there earlier of 248 watts from our previous section, previous slide right there. Now we're given our thickness of our skin fat layer, that's 0.003 meters right there. Now on the bottom here we have our K sub FF, our K value, thermal conductivity of the skin fat layer, which is 0.3 watts per meters times Kelvin right there. So we can see that watts cancels with that watts there, that meters cancels with that meters right there. Then this is times our area over here. Now we have this right here, 1.8 meters squared right there. So that rest of that squared cancels out with the other meters that we have down right here. And what we can see now is we're left with just a value of Kelvin, which is exactly what we want right there. So we want to make sure we do, if this is in Kelvin right here, as we did that unit analysis out, now what we want to make sure is that this right here matches the units of this over here. So this was right here, our surface temperature is given to us as 33 degrees Celsius. Convert that to Kelvin first, then we can add those two together, 306 Kelvin plus our 1.4 Kelvin right there. So this would right here would be 307.55 Kelvin, or if we converted back to Celsius, our T sub I right there would be 34.4 degrees Celsius. So now what we want to do is take a look at the heat transfer in the muscle. So this relates back to our bioheat equation, or equation 3.114 on page 179 of our textbook. We have this general form that we want to use here, which we have the second derivative of our theta term with respect to x right there, or d squared theta dx squared, minus our m tilde squared times theta is equal to 0 right here. So this is a simplified version that I really like to start with, that real general form right there, and then we can plug in for that. What we have for theta, or our excess temperature right here, our T minus TA right there, minus now this Q dot M over our omega rho B times CB right there. And now we have for our M tilde squared relationship here, we have omega times rho B CB all over our thermal conductivity K. And we can relate back to our diagram, which I've shown back up here again. So now we're going through that muscle layer right there. So we can see there's our TA that we're using right there to get to our other temperature over here, T. And we can see, okay, there's our thickness of our muscle layer right there. Then we have our other terms, our K sub M right there that we're going to plug in. So this is our general equation right here, 3.114. So let's go to another example problem. This is a very involved problem right here, so I would highly recommend going back through the derivation they do in this example 3.12 in your textbook on page 180. If there's any steps along the way that you're curious about the individual derivation breaking down these equations. Again, these are very complicated, specific equations for this problem right here, but I'd like to start with that general form there and plug in for it. So we can go down in that problem 3.12, the example problem, our textbook on page 180, take a look at a slightly modified version of what they show in the relationship for equation 2 right there, and we can come up with, now we can see we have a relationship here for when x is equal to Lm for our q value there, and we can do that there whether in terms of dt dx or if it's in terms of d theta dx right there. Then we come up with this right here for our q value equation right here. We have this general equation again. I would recommend going back through that derivation from equation 3.12 in your textbook as well. We have q, x is equal to m, is equal to a negative km. So there's our thermal conductivity in our muscle right there. Again, we're going through that muscle layer, so always remember what we're doing. So I like to write that down on the top of the page, just the heat transfer in the muscle. So that's for my K value for my muscle. Then I have my area times my M tilde right there, times now we have this ratio right here on the numerator. We have our, for our specific equation, our Theta sub I right there, times the hyperbolic cosine of our M tilde right there, times Lm, minus our theta sub C right there, all over the hyperbolic sine of M tilde times our L sub M right there as well. So again, L sub M is that length, that width, the thickness of our muscle layer right there. So now for this here, we can even plug in and make this even more involved right there. So again, that's why I like to start in general terms, because it's going to get more and more involved, longer and longer as we start plugging things in. So for our Theta sub I, we can use our general governing equation up top here for theta, for excess temperature right there. So theta sub I is T1 minus TA right there. Or sorry, Ti minus Ta right there. So there's our Ta, Ti right there, and we can plug that in right there for our values right there. So I have our Q dot M for our muscle layer all over our omega times now our rho sub B, rho sub P. Then we can do this thing again for our theta sub C right there. So we plug in for that value right there, and this is Tc minus T sub A right there. Plug that value in right there. And we can see this is minus now our Q dot sub M over our omega times rho sub B, rho sub A. So again, sorry, this is a minus up top here as well. So T1 minus TA, the temperature difference, minus this relationship here, and Tc minus Ta minus this relationship right here for our theta sub I and our theta sub C. So now we keep going, and now you can see how easy it is to get lost in this. So take your time, do this out step by step by step. But this is a very long, involved process and equation. To solve this right here, we can plug back in now for this Q, where x is equal to that thickness, our L sub M, right there, the thickness of the muscle layer. Now start plugging in for our theta sub C and our theta sub I terms right there. We end up with this relationship that we see here. So now what we want to do is we want to eventually get our Q dot sub M by itself right there. And we can see there's one right there and one right there. So how do we do that? Well, first thing we're going to do is we're going to multiply both sides by this hyperbolic sign, or M tilde Lm, which is on the denominator. Multiply both sides by that. Then once we have this over on this side multiplied over there, then what I want to do is divide by this K times this term right here, our A sub M, A times M tilde right there. So divide that over the other side as well. So what we end up with is this relationship here once we do both of those things. So now our left side of our equation is our Q right there times the hyperbolic sign M tilde Lm right there all over our value here for a negative value right there, Km. And yeah, that's a negative right there as well, times our A sub M A M tilde right there is equal to, now we've reduced down our right side by eliminating the denominator and that Km term up top there. So we end up with Ti minus Ta, temperature difference, minus, there's that ratio again there with our Qm, times the hyperbolic cosine of M right there times our Lm, our thickness of our muscle, minus now our temperature difference there, minus this Q term over here, like this here that we saw before. So those are now plugged in for our theta terms now into that, where those two terms came from there. So now what we want to do is solve this for our Q dot M, which is a long, involved process. This is something where maybe MATLAB is the way you want to do it. maybe Excel, maybe do it by hand, but there are quite a few steps getting from here to here where you really want to keep track of all those variables. So we do that, and we end up with a relationship here of Q dot M is equal to all of this here. So I can start plugging in, and then even this, there's some M tildes in here which make this even more complicated. So rather than making this more complicated and plugging all that into this and making this even longer so you can barely fit it down a sheet of paper sideways, let's get a numeric value for that. Let's plug in our known values right there for all of this to get this value here. So we plug those in right there, and we can plug this in. This is our 0.005 units of inverse seconds right there. Then we have our rho sub B right here. We plug in as 1,000 kilograms per meter cubed right there. Then we have our C sub P, which is 3,600 joules per kilogram times Kelvin, all over our K sub M value, or thermal conductivity of the muscle layer, which is 0.5 watts per meter times Kelvin, all to the 1/2 power right there. We get our M value right there. So this is equal to 60 in units of 1/meters right there, which then we can go back in and plug those into those locations there as a numeric value and not lengthen and complicate this equation for our Q dot M any more than we already have. So now what I've decided to do is kind of break it down. As I start plugging in those values for that M that we just solved for numerically, let's do that in a very strategic way so we can find other portions, other chunks of that large equation, get numeric values and plug them back in. So that's what I do right here is I look at these two terms, our hyperbolic sine of our M times Lm, and then our hyperbolic cosine of M times Lm there, and plug in those numeric values. So I have a hyperbolic sine of 60 when I plug in that value there, to units of 1/meters, times our value here of 0.03 meters right there for M. So 1/meters and meters cancel right there. And I have the hyperbolic cosine, same thing, 60 and 0.03 meters. Units cancel again in that right there. When I take that, do out the math, I end up with, for this term, now a value of 2.94, and for this term, a value of 3.11. So this is why I said, whether you do it by hand, Excel, MATLAB, do it out in chunks along the way. Clearly state what you're doing. That way, somebody else can follow through your work. If you did drop a negative, you plugged in the wrong value, your units were off, something like that, it's bound to happen to all of us as we're going through with this many variables and this long involved of an equation right there. Do them all separately. So that's why I've done this separately. And then I'm going to plug those back into my Q dot M equation, which is exactly what I'm stating I'm doing right here. So I'll plug those values back in right now, right there. And I now have my Q dot M is equal to, when I start plugging in my known values right here, there's my 0.0005 units of inverse seconds times my rho value right here, times my density value right there, plug in those. This is all times now. I can start plugging in all my other values right there from my Q dot M equation. So I now have 248 watts over my 0.5 watts per meters times Kelvin times my area of 1.8 meters squared. Now times that M term right there, 60 inverted meters right there. Now I can plug that in. This is where I plug in my 2.94. I plug that in right there. Times my temperature difference. I know those temperatures right there. And I leave this in Celsius because it's just a difference in temperatures right there. Times this 3.11. So I can plug that now in there, which reduces this down there. All over, there's again that 3.11 times my value right here now, plus 1. So now I can actually get a numeric value of Q dot M is equal to 2,341 in units of watts per meters cubed. So again, do your unit analysis out for all this and double check it and make sure that is correct. And I'd also recommend having that generic equation for Q sub M up on another slide right next to you there so you can reference back as you're looking at your setup page. You'll literally have all three of those pages next to each other. Your setup page with all your values, your page with all your general form for your Q dot M equation, and then all these values right here you can start plugging into this equation right here now to get your final numeric value down here for your Q dot sub M. So a lot of going on right here. Make sure to break this down, solve each section individually, maybe even more broken down than what I've done here in order to keep track of things. And this is a good one here where you're at that, do I switch over to numeric solver or do I still attempt this by hand situation? You can still do it by hand, but I would almost suggest maybe Excel would be a great spot so you can solve these. Might be a little bit more time setting it up, but once you have it set up, you are a little bit less apt to make some of these errors of your hand calculations there. And you can solve for each term separately in Excel within different cells and plug them all into your one general equation at the end here in order to get this value here for your Q dot M. So as we continue to wrap up Chapter 3, I want to take a look at the topic of thermoelectric power generation. So looking at the nature and rationale of this here, what we want to consider is that for many materials, when a temperature gradient is established, a corresponding voltage gradient is then going to be induced. So this is for a constant property material right here, and leads us to equation 3.115 in our textbook now. So we can see right here on the left-hand side of this equation, 3.115, we have our voltage difference right there. So this is our E1 minus our E2, and this is equal to, what you see on our right-hand side, our temperature difference over here, our T1 minus T2 right there, times this coefficient right here. So this is the Seebeck coefficient. Now, if we take a look at our units right here, we want to do unit analysis, and if this is to balance right here, the units of the Seebeck coefficient are volts per Kelvin, which makes sense because right here, our left-hand side over here is in volts, our temperature difference is Kelvin, so having this right here as our units is going to make it balance out for our unit analysis. So now we can ask ourselves the question, well, what is this Seebeck coefficient? This coefficient is a material property that representing the proportionality between the voltage and the temperature gradients right there, which we can see that's pretty much the definition of what we can see from this equation 3.115. Now, a couple things to note with the Seebeck coefficient. This coefficient can be small in metals, but can be relatively large in semiconductors, so varies with the type of material that you're using. The Seebeck coefficient can also be made to be positive or negative by doping a semiconducting material. So when P and N-type semiconductors are arranged in an electric circuit, including an external electrical resistance, which we have here, it's a variable R sub E load right there, the voltage differences can drive an electric current I. So we can actually utilize that to drive an electric current. So now as we continue on to the topic of thermoelectric power generation, we want to take a look at here is a simplified thermoelectric circuit consisting of one pair, so N is equal to 1, of semiconducting pellets right here. So we can see that illustrated in this diagram below here. So what we can see is on the top and the bottom of this, so we have this thin metallic conductor. So we can see that thin metallic conductor right there. And in the middle, we have the semiconductor. Now on the left side right here, we have our N-type semiconductor, our S sub N. And on the right side, we have our P-type semiconductor, S sub P over there. Now we can see this current flowing through in our diagram right there, going through both of these, up through our N side, up through that thin metallic conductor, back down here through our P-type semiconductor, into this bottom thin metallic conductor right there, back around. There you can see there's our RE load equivalent right there. Now we can see at the top here, we have this T1 at the interface between the thin metallic conductor and our semiconductor there. And at the bottom, we have this T2, our temperature, and our voltage right here, our E2 right there, between, again, that thin metallic conductor and our semiconductor now down at the bottom right there. So what we want to discuss next is these thermoelectric effects also generate or absorb heat at the interface. So that's where that T1 and that T2 are right there between these dissimilar materials. Again, those dissimilar materials being the thin metallic conductor and that semiconductor material right there. So that leads to the discussion of Peltier heating right here, or our Q sub P. Now this is going to be positive at the hot side of the material, our T1 right there. So there's our T1 on the hot side right there. And it's going to be negative at the cool side, our T2. So there and here is our cool side, our T2 right there, as described with our T expressed in kelvins right there. So we're going to be using Kelvin as our units for our temperature right there. So this now leads us into our governing equation down here to solve for that Q sub P, or Peltier heating right there, from equation 3.116 in our textbook right there. So we can see right there our Q sub P is equal to that current I times the difference right there between SP and SN, where we have these correspond to the P and N-type semiconductors. So we can see, go back up top here and see SN and SP right there. So it's our SP, our P-type, minus our SN, our N-type right there, times that temperature. Now this is equivalent to our current right there, times this differential Seebeck coefficient SP-N, which corresponds to that difference between those two, times our temperature T. And again, this corresponds to equation 3.116 in our textbook. So now let's talk about Q1 right here. So heat transfer to the circuit is this Q1, but because thermoelectric power is generated by the circuit from this relationship here, we've seen from EE classes right here, that P is equal to IR squared, where IR is our load right there, that our heat transfer from the circuit must be that Q2 is less than our Q1 value right there. So we can go back up to our diagram right here. We can see our Q2 right here, half on each side, Q2 over 2 right there, and there's our Q1 up top right there. So in order for this, it must be that Q2 is less than our Q1 right there. So now if we're talking about the hot side of our circuit up top right there, we can see an energy balance is going to yield our equation 3.119 in our textbook right here. We have Q1 from the top side right there, the hot side right there, which is going to be equal to our, here we have this term right here, Q where X is equal to negative L, where heat conducted into the semiconducting material right there. So there's our negative L right there at that point right there, plus our Q sub P1 right there. So we can see that. There's that relationship right there. It's equal to Q on X is equal to negative L, plus now we have I times this right here for the Seebeck right there, for that difference right there. So Seebeck coefficient right there for that difference between P and N right there, times our T1, where that's our T1 at the top surface right there. So this goes back to our equation 3.119 in our textbook. So now we want to take a look down here on our cool side at the bottom of our diagram right here. And we can see we have these Q dots right here. So we want to consider is that we also have ohmic heating occurring down here right there. So this is based off our relationship here, I squared Re right there, and this is in the semiconducting material. So now this goes back to this Q dot. We can form this from equation 3.117 in our textbook right here, where we have on the numerator, we have this I squared times rho ES right here, where this is the electrical resistivity of the semiconducting material, units of ohms times meters right there. And then on the base right here, we have this A squared C comma S, which this is our cross-sectional area of one semiconductor pellet right here in units of m squared right there. So again, this relates back to our equation 3.117 in our textbook as we're talking about this ohmic heating. So now if we assume constant properties and are using equation C7 right there, the heat conducted into the semiconducting material at the hot side, so we're talking about the hot side here, is given by the following equation down here, which comes from equation 3.118b in our textbook right there. We have our Q when X is equal to negative L at the top there at the hot side. Is equal to 2 times, there's that A sub CS that we just talked about there, times now we have our Ks over 2L, where Ks is the thermal conductivity of the semiconductor material right there. So that's where we put that in. S is for the semiconductor material right there, times our temperature difference between T1 and T2, minus, now we have this term over here again, we have our I squared times our rho E comma S times L, all over that same A sub CS squared right there. So this again references back to equation 3.118b in our textbook. So now assuming that that thin metal conductor at the top there posed negligible thermal resistance, and there's also one at the bottom as well, both these we're assuming are composing negligible thermal resistance, and there is no contact resistant effects right there. So two rather large assumptions with that there. We can combine equations 3.118b and 3.119 and get the following relationship right here that we see in equation 3.121 in our textbook right there. So we've combined 3.118b and 3.119 to get this relationship shown here. So this gives us a value for our Q1 right there if we reference back to where that is in our diagram from the previous slides. And we can see here there's that ratio right there of our AS and our KS for the semiconductor thermal conductivity right there over L times the temperature difference right there, plus our I, our current times that, there's our Seebeck coefficient for the difference right there, Pn, times our T1 minus 2 times, now we have this relationship over here, I squared times our rho ESL all over that A comma CS right there. Now we can do the same thing on the cool side. So all this up here before was for the hot side of our circuit up top there. So this up here, all up here is for the hot side. Now come down here, we can talk about the cool side of the circuit when we're dealing with, rather than T1, we're dealing with T2 down at the cool side of the circuit there. So that comes up with our equation now 3.122, which is similar to 3.121, but now it's for the cool side down here. So we can see now we're solving out for our Q2 right there, and there are some subtle differences throughout this equation as well. So the next thing we're going to do is do an energy balance on the entire circuit right there. And from that energy balance, we can get the electric power produced in the circuit, or our P, by the following expression right here, where P is equal to Q1 minus Q2, which relates back to equation 3.123 in our textbook right there. And we just saw on the previous slide, we had relationships for Q1 and Q2 that we can reference back to as well. Now, if we combine equations 3.121 and 3.123 above right here, then what we can get is this relationship shown in 3.124. We have P is equal to that current times that Seebeck for P dash N right there times that temperature difference minus now 4 times we have the numerator up here of I squared rho ESL all over that A CS right there. Now this is equal to, now we can reduce this down a little bit more right there, and you can see what we've done now is this last term changes right there. This first term right here still remains the same as we saw before, our I times the Seebeck coefficient times the temperature difference, but now we have 2 times our I squared R 2 I squared times R ES right there, and this is for equation 3.124. Where this comes from right now is the fact that when the electric power produced by the circuit is consumed in the load right there, then we have this relationship right here of P is equal to I squared RE load right there. So at this point, we've derived a lot of different equations for specialized applications. Now, one thing we want to consider is that the textbook does a good job of going through how we derive those equations. We've done a little bit here within the lecture here. We've said, okay, we're going to plug this equation in with this one or combine these two equations to get this new equation for this special application. But I would highly recommend going back to the textbook and really looking through those derivations and understanding why and how we do them for each application. So as we continue on now with thermoelectric power generation, let's take a look at equation 3.121, 3.122, and 3.124, and these can be generalized for a thermodynamic module consisting of n pairs of semiconducting pellets. So now we have several different pairs of these semiconducting pellets as compared to our last diagram. We're just looking at one pair right there. So we can see this down here in our diagram. And one thing to note within this here is we can now see these thin ceramic insulators. So a layer of these thin dielectric material, in this case ceramic, sandwich the module to provide one, structural integrity, and also electrical insulation from the surroundings. You can see on the outside here we have these two layers right now of these thin ceramic insulators, but then also inside of those we've seen before are thin metallic conductors. So we use these insulators right here again to sandwich the module to provide rigidity and to insulate it from its surroundings. So now we're going to take a look at a couple specialized equations here for our Q1, Q2, and P sub n, where P sub n is the electric power generated by the module right there. So let's go back up to first here for our equation for Q2 right here, which relates to equation 3.125 in our textbook right here. So we can say that Q1 is equal to, now we have our temperature difference right here on the top between T1 minus T2, all divided by this conduction resistance of the module right here. We have our general equation right here for our R sub T that we're seeing right there. And this should be familiar from what we've seen before. We have our L right here divided by our N, which again is that number right there for the number of pairs right there, times our A sub CS that we just talked about, and then we have our K sub S right there as well for our thermal conductivity of the semiconductor material right there. Now this is plus right here, our I, our current times right here, our effective feedback coefficient. So there's that effective feedback coefficient right there. And again, you can see right there, this is equal to now our N times our SPN right there. So to get this relationship right here, for this right here, for the effective feedback coefficient, we multiply N right there for the number of pairs times the S feedback coefficient for SPN right there. And this is times our T1 minus our I squared times our REF, or electrical resistance of the module there. So that kind of breaks that down. And I think this is important to do as we're looking at these equations, not to freak out. It's like, oh my gosh, there's so much going on right here. But look at them term by term. Okay, I've seen this term before. I've seen something similar to this, and I know how to relate it back to something else I know. Okay, I know what this is. Okay, I can figure out another equation that this is related to, and break them all down that way and deal with them part by part until we can wrap our heads around exactly what we need to solve for, or what variables we're going to need to plug into this equation to solve for whatever it may be, in this case our Q1. Now we can go down here and we have the same type of relationship here for our Q2, which goes to equation 3.126 in our textbook as well right there. So we have the same thing with a couple of little differences here. We can see now we're dealing with T2 rather than T1 as we go through and plug into this relationship as well to get our Q2. And last we have down here our equation 3.127. So this one here, we're looking for P sub n, or electrical power generated by the module. So we can see this is equal to Q1 minus Q2. So we can simply take this relationship up here from 3.125 and 3.126, just as I talked about, combining equations to form another equation right there. And when we do that out, what we find is we have this relationship shown here. And again, this relates back to equation 3.127 in our textbook. So now let's take a look at an example problem involving thermoelectric power generation. So in this problem right here, they tell us that the electric power generator for an orbiting satellite is composed of a long cylindrical uranium heat source that is housed within an enclosure of a square cross section. So the only way the heat that is generated by the uranium to leave the enclosure is through the 4 rows of thermoelectric modules that we can see down here in the diagram below in example 3.13 in our textbook right there. So the thermoelectric modules generate electric power and also radiate heat into deep space by the following condition right here, that T surround is equal to 4K right there. So consider the situation where there are 20 modules in each row for a total of 4 by 20, or 80 modules right there. So M is equal to 80 modules. The modules are wired in series with an electrical load of an RE load right here given to us as 250 ohms, and have an emissivity right here as epsilon is equal to 0.93. So they want us to solve for a couple things. They want us to determine the electric power generated for E dot G is equal to 1 10, and 100 kilowatts, and also determine the surface temperatures for the modules for all three thermal energy generation rates. So now that we've had the opportunity to read through the lengthy word problem there, what we want to do now is simplify it down a little bit and create a concise word problem right here. So this goes back to problem 3.171 in our textbook right here. So this problem involved thermoelectric power generation with radiation cooling right there. So within this problem, we simplify down the wording of it here. We see we have a cylindrical uranium heat source used for power generation in space. Now the cooling of the thermoelectric modules is by radiation to deep space, so we have that 4K right there, and M is equal to 80 modules that are going to be wired in series right there. They want us to determine two different things. First, they want us to find the electric power for our E sub G right there, or our rate of energy generation of 1, 10, and 100 kilowatts. They also want us to determine the surface temperature of the modules. So two different things we want to solve for right there. And again, this is for three different cases, 1, 10, and 100 kilowatts for our E dot G right there for our rate of energy generation. So we can see now what we want to do is create a new schematic down here, a little bit more detail, a little bit neater. So we can see we have the module characteristics over here. So for the characteristics right here, we have the conductive resistance of the module right here, R sub T, which is equal to 1.736 K per W right there. We have our effective Seebeck coefficient right here, and we have a relationship for that as well, which this is equal to 0.1435 in volts per Kelvin right there. Then we also have our electrical resistance of the module right here, our E effective right there of 4 ohms. We know our dimensions are W by W right there. So we can see our W over here in the diagram is given to us as 54 millimeters right there. We can see the length of this right here is given to us as 2 times the length, or 2L is given to us as 5 millimeters right there. We have our insulation we can see down there. We have our thermoelectric module right here. So again, there's 4 of those in each one of these right there like that. And these have emissivity here of 0.93. And we can see our load right here of 250 ohms. And we can see the temperature of our surround right here. There's that 4K right there that we were discussing there. And this is for the rate of energy generation right here. So now within this, there's 4 different assumptions that we're going to make. First assumption we're going to make here is that it's one-dimensional steady state conduction. Second is that we're dealing with constant properties. Third is that we're dealing with large surroundings, dealing with space, so that's accurate right there. And fourth, the module thermal resistance is dominated by the semiconducting pellets. So these are the 4 assumptions. Here's our problem statement, a simplified diagram with all the information we need in that there, all coming from that wordy problem that we read on the previous slide there. So next what we want to do is take this information and go from there and create our setup page. So that's exactly what we do next. We take that information from that simplified word problem, that schematic, that nice neat schematic that we created right there, create our setup page. This is problem 3-171. Again, if this were a homework problem, you'd have your name, the due date, what the homework assignment was right there. Now we have your given information here. So temperature of our surround is equal to 4K right there. And we have our 2L, so 2 times that length is 5 millimeters. I want to convert that to meters right away. So that's 0.005 meters. We have W is equal to 54 millimeters, or 0.05 meters. Then we have our rate of energy generation here, E dot sub G, which is going to be 1, 10, and 100 kilowatts right there. Then we have our thermal conduction resistance for each module right there, so our R sub T conduction comma module right there of 1.736 units of K per W right there. We have our RE effective right there of 4 ohms. We have our RE of the load right there of 250 ohms. We have our emissivity given to us as 0.93, and we have our value here for our coefficient right there of 0.1435 in volts per K right there. And again, I rewrite out those same assumptions: 1D steady state, constant properties, large surroundings, and that the module thermal resistance is dominated by the semiconductor pellets. So now what we want to do is take a look at our thermal circuit for just one module right here. So that's what we have down below here in this diagram right here is our thermal circuit for this one module right there. So within this right here, what we can see now, this is our thermoelectric module right here. So we have up here our Q1. We have our equation for Q1 that we solved for previously, and this comes from equation 3.125 in our textbook on page 185. So we have this relationship right here for Q1, so we can reference back to that to see the derivation. We have the same for Q2. So Q2 we have from equation 3.126 on page 185 of our textbook, where this is our Q2 relationship right there. So you're up here. There's our Q1 coming in, there's our temperature 1 there, there's our Q2 coming out, there's our temperature 2 there. There's our resistance from radiation going down here to our temperature at our surround right there. Now, next what we have here is we can see off to the right, we have our PN, our electric power generated by this module. Again, this is just for one module here. So we have this relationship for our P sub n equation, and this comes from equation 3.127 on page 185 of our textbook right there. And this is equal to this equivalent down there like that. And you recall, we can come up here for our variables here. So our R sub D, R sub T, common conduction, common MOD is our conductive resistance of the module. Our S sub P dash N effective is our effective feedback coefficient, which is our number of modules times our S sub P dash N right there. And then we have our R sub B effective, or electrical resistance of the module. So those can all plug in where they go down here in these equations, 3.125, 3.126, and 3.127 as well. We also see right here now our Q1 is equal to, we can take a look at right here, for this right here, we have our E dot G right there, all over our M value right there, where our M is equal to 80 right there. So there's 80 of these. So we can take this E dot G divided by 80 for our Q1 right there. So as we continue on with our solution, let's take a look first for our Q1. So our Q1 comes from equation 3.125 on page 185 of our textbook right there. So we'll call this equation number 2 for future reference to plug back into with this here. So we take here, this is 1 over our R sub T. We can go over here, our R sub T right here is our thermal conductive resistance for each module right there, times our temperature difference between T1 minus T2, plus I times our S sub P dash N effective, which is our effective Seebeck coefficient right here by this relationship there, times T1 minus our I squared times our R effective, RE effective right there, which is our electrical resistance of the module right there. So this is equation 3.125 for our Q1. So from that there, we can go back and we have over here boxed off to the right over here is all of our equations from our setup page for our known values. So let's plug in our known values right there. So we plug in 1 over, well, we have that value there for our thermal conductive resistance for each module of 1.736 and K per W right there. So we plug that in at our denominator right there, times our T1 minus T2 plus our I times, now we have this value here for our effective Seebeck coefficient right there of 0.1433 in volts per Kelvin right there. So we can plug that value in here, times our T1 minus our I squared times our R effective right there. Our E effective right there is 4 ohms, or is our electrical resistance of the module right there. So we can plug that in there. Now from that, we can simplify, reduce for everything that's plugged in. We end up with what we're calling our equation 3 here, which is for our Q1. So we have T1 over T2 over that 1.736 times our plus our I times that 0.145 in volts per Kelvin times T1 minus our I squared times our 4 ohms right there. And they're calling this equation 3. So now we've basically taken our equation, what we're calling 2 right here, which is from equation 3.125 in our textbook, plugged in our known values, simplified it down to get this relationship in equation 3. Let's do that same process now for our Q2 value right here. So this is from equation 3.126 on page 185 of our textbook there. So we have 1 over that same value for our R sub T right there. So we come back over here, R sub T, our thermal conductive resistance for each module, plug in our known value for that right there, 1.76. We'll move this T1 minus T2 over on the numerator right there where that 1 is right there, multiply that through. Plus now we have our I term times our value here for our effective Seebeck coefficient, so we can plug that in of 0.1435 times V in units of V over K right there. Times now, this is a T2, so we'll leave that as a T2 there, plus our I squared times our value for our RE effective right there, or our electrical resistance of the module, which is our 4 ohms. So we can plug this in, and now we have that same relationship for Q2. So we've got a value for Q1 and Q2 with our known values plugged in. So we've got these two relationships here. They're called equation 3 and equation 4. Now, the next thing that we want to look at now that we've got Q1 and Q2 is the heat transfer by radiation to deep space right there. So we have this relationship here that we have Q2 is equal to HR times omega squared times T2 minus T surround right there. Well, now we can then go back in and plug in our known values right there. So we have this value for our omega term right there. So we can go back up. This is 0.054 meters. So we can plug that in right there. That's squared right there times T2 minus our T surround. Or our T surround is 4 Kelvin right there. So we can plug that in right there. So then we can go back down here and we say, okay, well, what is our HR? Well, our HR is given to us as equation 1.9, referencing all the way back to page 10 at the beginning of our textbook right there. And this is a radiation heat transfer coefficient right there. So we can plug in this right here. This is given by the relationship of our epsilon times our Stefan Boltzmann's constant right there times T2 plus our T surround times our T2 T2 squared plus our T surround squared right there. We'll call this equation 5 now right there. So we do this, plug in our known values. We'll have our epsilon value. We can go back up top. This is 0.93. That's our emissivity right there. We have our Stefan-Boltzmann constant that we can plug in. We know that value is 5.6 times 10 to the negative 8 units of watts per meter squared times Kelvin. Then we have our T2. We plug in that T2 plus our T surround, which is 4K, times our T2 squared plus our surround, which is 4K squared right there as well. So now we want to take a look and calculate our total power right here. This is the electrical power produced by all 80 modules. M is equal to 80. So we have this relationship down here. We have M times our P sub n, or the total number of modules, 80 modules times our P sub n, where P sub n is the power generated in each module. And this is given in equation 3.125 on page 185 of our textbook right there. So that, if we go to 185 of our textbook, take a look at that equation, 3.127. We have P sub n is equal to I times right here, our value here for our effective Seebeck coefficient, times our temperature difference between T1 minus T2, minus 2 times our I squared times our value here for our electrical resistance of the module right there. So we take all of this and we plug it up in here after M. So this right here comes up and now goes right there like this. Now this is equal to, if we take a look on page 188 of our textbook right there, we have this relationship that this is equal to I squared times our RE load right here, which is our 250 ohms given to us in our problem statement right there. So this right here would say that our total power right there, or our electric power produced by all 80 modules, is equal to our I squared times our RE load right there, which we have a value for with this here. So what we can do is we can rearrange this now and say that this is equal to this right here. So we do that there, and now we have this relationship right here by combining those two equations right there. And when we have that, now we can start plugging in our known values. So we go back over here, which we have here is all of our given information from our setup page right there. Our known values are M is equal to 80. This is I comes down here. We don't know that yet. Then we have here our effective Seebeck coefficient. We have that value for that of 0.1435 in units of volts per Kelvin right there, times our temperature difference of T1 minus T2, minus 2 times our I squared, which we still don't know our I value yet there, times our RE effective right there, electrical resistance of the module, which is 4 ohms. Now this is equal to our I squared times our 250 ohms right there from this value right here that was given to us in the problem statement. So now we're going to call this our new equation number 6. So now the reason we labeled these is because we now have 6 equations and 6 unknowns. Well, we can reduce one of them there because we have this relationship here from equation 1 that Q1 is equal to our E sub G over 80 right there, and we're given 3 values for E sub G. So we can do this for all 3 times of our Q sub 1 right there for 1 watt, 10 watt, and 1 kilowatt, 10 kilowatts, and 100 kilowatts. So we can get values for each Q1 for each of those. So that will leave us with 5 equations and 5 unknowns to solve 3 different ways right there for each of those values. So that leaves us, again, 5 equations, 5 unknowns. What are our unknowns? We have all 5 equations. We've labeled them. And our unknowns are T1, T2, I, Q2, and HR. Now we can solve each of these equations. 5 equations, 5 unknowns. We need to decide them simultaneously, but it matches. The number of equations matches the number of unknowns, so it's possible. So you can do this out by hand if you want to spend another 10 or 15 pages of hand solutions and potentially dropping negatives and losing a variable and plugging things in and getting really ugly, but it is possible. 5 and 5 is not impossible to do by hand. You could do MATLAB, you could do it in Excel, or you can even do it in Python, or whatever your numeric solver of choice is. I've chosen to do this in MATLAB, and I've included my code right here for you for this here, for our MATLAB's code for 5 equations, 5 unknowns right there. So I write all of these out down here. You can see my F equation for my function right there. I go through all of this right here and plug this. So this is, if you want to try to solve this with MATLAB, here's the code that you could try typing in and doing this yourself to get our values to solve for all 5 of these unknowns right there. So with the specification of the E sub G from equation 1 right there, we can solve that for our Q1 values, plug those in, and equations 2 through 6 can then be solved simultaneously using that code that I showed from MATLAB, or by hand you could solve them, or again Python, whatever your numerical solver of choice is. And you can solve for your T1, T2, I, Q2, and H values there in order to get this information down here. So we have that E sub G right there, so you can plug those in for E sub G to get that Q1 right there. And then now you can get your I sub A, your power that it asks you to solve for, your temperature too, and your efficiency as well if it asks you to solve for any of that. For each of these cases, you want to solve it through 3 different times. Again, for each of those values for your E sub G from 1 to 10 and then to 100 for kilowatts right there. So as we finish up chapter 3, the last section we're going to take a look at here is micro and nanoscale conduction. So if we reference back to chapter 2, we recall that conduction will be viewed as a consequence of energy carrier motion, particularly looking at a molecule, electron, or a photon right here. So as these energy carriers collide with each other and with the physical boundaries, this is going to affect the propagation and the heat transfer rates. So what we can see down here in this figure that we show below is we have molecular trajectories in part A over here on the left-hand side, a relatively thick gas layer, and on part B over here, a relatively thin gas layer right there. So the molecules collide with each other and with the two solid walls. You can see the solid walls on either side of this, either where in part A right here we have the thick gas layer and you see all those molecules in there, or in part B where we have the thin layer over here. Those are two boundary layers, and you don't have quite as much right there as far as the collisions go. So the gas molecule motion between the two isothermal solid walls, we can see their solid walls right there. We have TS1 and TS2. So TS1, TS2, TS1, TS2 right there. The separation distance between the walls, where L1 is greater than our L2 right there. So the molecular wall collisions become important as this length right here, L over our lambda right here, where lambda is our mean free path length in nanometers right there, becomes small. So as that becomes small, this molecular wall collisions become important right there, affecting the heat transfer by conduction through the gas layer. So our QX right here is going to be affected by that. So as we continue on with our topic of conduction in a gas layer right here, we want to take a look at the collision and scattering of a gas molecule with a solid surface. So this is described by a thermal accommodation coefficient. So our thermal accommodation coefficient is given the variable name here, alpha sub t. So this alpha sub t is equal to the relationship that we can see in equation 3.130 in our textbook there. So this is equal to, if we take a look at our numerator right here, we have T sub I minus our T sub SC, where T sub SC is the molecule temperature leaving that surface. Now if we go down to the denominator right here, our T sub I over here, this is the molecule temperature prior to collision with the surface. So that Ti is the same on the top and the bottom, our numerator and denominator there. And then our T sub S, this is minus the T sub S. Our T sub S is that surface temperature. So we have three different temperatures that we're looking at here. We're looking at the molecule temperature prior to collision, our T sub I. Then we're looking at our molecule temperature leaving the surface right there, our T sub SC. And we're looking at the surface temperature itself, our T sub S right there. So let's take a note down here. When we have our alpha sub t right here, or our thermal accommodation coefficient equal to 1, then our T sub SC, or as we saw here, our molecular temperature leaving the surface, is equal to the temperature surface. So when our A sub t is 1, these two are equal to each other. Now, the other case here, when our A sub t is equal to 0, then our T sub SC is equal to T sub I. So our molecule temperature leaving that surface is equal to our molecule temperature prior to colliding with the surface right there. So those are the two cases on either end of the spectrum where A sub t is equal to 1 or A sub t is equal to 0. So now let's look at the situation where we have an ideal gas. If we have an ideal gas, and this molecule-to-molecule and molecule-to-surface collisions may be associated with thermal resistances. Now this is related back to equation 3.131 in our textbook, where we have our Q sub x is equal to, if we take a look at our numerator right here, so that's the difference in our surface temperatures, TS1 minus TS2. Now in our denominator right here, we have this thermal resistance plus this thermal resistance here. We have this R sub T MM and R sub T MS right here, which relate back to equation 3.132 A and B. Now I would recommend going back to these equations and taking a look at this section in our textbook in order to get an idea of exactly how we do these derivations and what these variables relate to. But if we look at this right here, our R sub T MM is equal to our L over our Ka, which is our thermal conductivity times that area there, and our R sub T MS. Now this breaks into effect here our mean free path as well as our thermal conductivity over area there. So instead of L, we're using this relationship here. And then we have this whole term involving that A sub T or alpha sub T, which we talked about above up here, which is our thermal accommodation coefficient right there, our numerator and denominator there, as well as this gamma term right here. Well, this gamma term down here is given by the relationship of C sub P over C sub V there. Now, a thing we want to note with this relationship here is our Q sub x right here. This is going to approach this K sub A over L relationship times that temperature difference between our surface temperatures right there as our mean free path over that L distance right there approaches 0.